Okay, so welcome to this next video in the playlist on group theory. So we've now looked at quotient groups, okay? So we've looked at how, in a sense, you can divide one group by a normal subgroup that is within it, okay? To construct a new group called the quotient group. What we're going to look at in this video is the concept of product groups, okay? Which is kind of analogous to multiplying groups together, basically. Okay, so we've looked at dividing groups. Now what we're going to look at is how we can multiply groups. Okay, so just as division makes something smaller, multiplication makes something bigger usually. Okay, and indeed, just as taking a quotient group makes a smaller group, okay, so whenever you have one group and you divide it by a normal subgroup, you end up with a much smaller group. The quotient group is much smaller than the original group. Now what we're going to see is when we're taking product groups, we're going to end up with bigger groups, basically. Okay, right, so to construct a product group then, you firstly need to start off with two groups that you are going to multiply by one another. Okay, so we'll start off with two groups, so we'll just call them arbitrarily capital G and capital G prime. Okay, and these are just any two groups, okay? There's nothing necessarily related about these two at all. They are just two groups. So they're both sets of symbols, completely unrelated symbols potentially, with composition laws on them. You can make these whatever you like. Okay, and what we're now going to do is we're going to multiply these groups together, basically. Okay, so we're going to construct what is called the product group of the group G with the group G prime. So we'd call this the product group of G with G prime, basically. Okay, and it's written like so: G multiplied or cross G prime, basically. Okay, so we're going to construct this product group of G with G prime. Now, a group then is a set of symbols with a composition law defined on it. So firstly, what I need to do is tell you what the set of symbols is going to be that's going to form this product group. And then what I need to do is tell you what the composition law is going to be. I need to tell you how to compose any two symbols within the set together. And then I need to prove that this composition law that I'm about to define actually obeys the axioms of group theory, because this is going to be a group, basically. Okay, right, so let's start off by studying the set that we're actually going to use to define the composition law on. Okay, so this is going to be the set containing all ordered pairs of elements from the group capital G and the and the group capital G prime. Okay, so it's going to be the set containing all ordered pairs little g prime, like so, where little g is an element of the group capital G, and little g prime is an element of the group capital G prime. Okay, so quite simply, what you need to do is you need to go through every single element of the first group, capital G, and put that in this first socket here. Okay, and then what you need to do is for every single element of the first group that you put in here, you need to let this second element in this ordered pair, which is an element from the second group, capital G prime, it needs to vary over all capital G prime. So basically what you do is you take every possible combination of an element from the group capital G and an element from the group capital G prime, and you stick those into a set. So let me repeat that. You have every single combination that you can possibly dream up of an element from the group capital G with an element from the group capital G prime, basically, in this set. So you have effectively taken the Cartesian product of these two sets, okay? And that's the set that we're going to use to produce the product group on. So all I now need to tell you is how we're going to define composition on this Cartesian product set of the set that underlies the group capital G with the set that underlies the group capital G prime. Okay, right, so let's take two arbitrary elements from this set and I will show you how to compose them together. I'll define the composition. Okay, so let's have one element which we'll call little a prime. So little a is from capital G and little a prime is some element from capital G prime. And now what I want to do is compose this with another element which will have little b little b prime, where again little b is some element from capital G, and the primed element here is from capital G prime. Okay, and this composition here is now the composition that I am defining, so pay close attention. This is a definition that I'm making here. Okay, so this is the composition in the product group that I'm about to define. Okay, so how am I going to define then composition of these two elements of this set together? Okay, well I'm going to define it using the composition laws that we had on these groups. So what I know is that we have a composition law on the group capital G involving elements of capital G, and we have a composition law on the group capital G prime involving elements of capital G prime. So a natural thing to guess that we would define this to be equal to is just compose things component-wise. So compose the first two entries here together in the group capital G, okay? So what I'm going to do is I'm going to compose A with B, okay? A and B are both elements of this group capital G, and this composition here will now be composition in capital G, so I'll colour code capital G here in blue. Okay, so you compose little a with little b, they're both elements of capital G, and you're going to compose them together in capital G to get another element of capital G, which will be the thing that you put in the first socket of the ordered pair, basically. Okay, then what you'll do is you'll do the same thing for the second socket of the ordered pair, so you'll compose A prime with B prime, and this composition now will be in the group capital G prime, okay, because both A prime and B prime are elements of the group capital G prime, so you can compose them together in that group, okay, to get another element of that group. So hopefully you'll agree now that whenever I compose two elements of this set together, I will end up with another element of this set, and that's simply because these are groups and therefore the composition laws on them are closed. Okay, so whenever I compose two elements of the group capital G together, I'll get another element of the group capital G, so A composed with B here is another element of capital G, and whenever I compose two elements of capital G prime together, which indeed I have, I'll get another element of capital G prime, so I've put an element of capital G prime here. So this must now be another element of this set, because this set, remember, contains every possible combination of one element from capital G and one element from capital G prime. Okay, so we already know then that this composition law is going to obey the first axiom of group theory, which is closure, so I'll tick that one off straight away. Okay, so we need any elements, any two elements from this set composed together to be equal to another element of the set. I've just talked you through that, so we can tick that one off straight away. So closure is done. Okay, we now need to make sure of the other axioms of group theory. Okay, so next let's go on to the second axiom of group theory, which is associativity. Okay, so remember, associativity is all about how you compose three things together, okay, because obviously this composition law doesn't define how you compose three things together, it only defines how you compose two things together. So if you want to compose three things together, you have to split the composition down into composition of two things. Okay, so let me write this out. So let's say we have some A prime, and we want to compose it with B prime, and we want to compose that with C prime. So we want to compose three things together in my new product group, basically. Okay, like so. Well, of course, this composition law doesn't define how to do that. What you would have to do, if you actually wanted to compute this, is you'd have to put brackets around it. You'd either have to put the brackets like so, okay, which means basically you first compose these two together, and now that's a composition of two things, so that's defined with this composition law. You'll then get an answer which is just one ordered pair. You'll stick that in this blue socket here, okay, and then you'll compose that with this C prime now, okay, and that will again be a composition of just two members of this set, basically, and that will therefore be defined by this composition law. Okay, right, so you can either put the brackets around like that, or you could put the brackets around like this, which means firstly compose B and B prime with C prime, okay, and that's a composition of two things, so that can be done using this composition law, get the answer and then compose A prime with that answer. Okay, another composition of two things. So there are these two ways of actually composing three things together, okay, by putting the brackets in different places. If associativity is true, it should be the case that it does not matter where you put the brackets, that the composition of three things has one and only one answer, basically, should be the case if associativity is true. Okay, so it shouldn't matter where you put the brackets. Okay, so how are we going to prove this? Well, associativity is going to come directly from associativity of the compositions on the group elements in capital G and capital G prime. So quite simply, to show this, let's just go through the two options here. Okay, so either using blue brackets or turquoise brackets and prove that they give the same thing. So we'll start off with blue brackets. Okay, so we're firstly going to compose A prime with B prime, and then take that answer and compose it with C prime. Well, we already have the answer to what A prime composed with B prime is. It's up here. So let's just take this and now compose it with C prime. Well, of course, we still do this component-wise, so what we'll end up with then is A composed with B, the answer to that composed with C. Okay, so we're multiplying this component here with this component, C, and all of these compositions here are compositions in the group capital G there. Okay, so I'll try and colour them in blue here. Okay, and then the second component is then going to be A prime composed with B prime and then composed with C prime. So what we'll get is A prime composed with B prime and then the answer composed with C prime, like so. Okay, and all of those compositions will be in the group capital G prime, so we'll colour those in turquoise like so. So this is what we get if we put the brackets in position blue here, and you can probably already guess what we're going to get if we do it with the brackets in turquoise here. Okay, but let's do it anyway. Let's spell it out nice and slowly. Okay, so if we firstly multiply BB prime with CC prime, what will we get? Well, I might just write that out up here. Okay, so we'll get B composed with C, where this composition is once again a composition in the group capital G. Okay, and then we'll get B prime composed with C prime, where this composition is then composition in our group capital G prime. And then what we're going to do is we're going to compose A prime with this. Okay, and what we'll then get as our final answer is A composed with B composed with C, so the answer here, so multiplying this component by this component, where all of these compositions are in the group capital G. And for our second answer, we'll get A prime composed with B prime composed with C prime, like so, where all of these compositions are in the group capital G prime. Okay, now these two things are always going to be equal to each other because of associativity in the group capital G and the group capital G prime. So associativity in capital G tells us that these two things are exactly equal to one another. Okay, and associativity in capital G prime tells us that these two things are exactly equal to one another. Okay, so because of associativity in the two groups that we use to construct the product group, we get associativity in our new product group, basically. So that's nice and easy then. Okay, so associativity, we do have associativity if we use this composition law that I've just defined on this set of ordered pairs then. Okay, right, so next axiom of group theory, axiom number 3, we need an identity element, an element that will compose either on the left or on the right with any other element to give back that other element. Okay, right, so I'm just going to tell you what the identity element is actually going to be in this product group, but I hope it should be pretty obvious. Okay, so quite simply, the identity in our new product group is going to be where we have the identity from the first group in the first position, and then we have the identity from the second group, capital G prime, in the second position. So quite simply, these two groups are groups, so they have an identity element. Take the identity element from G and put that in the position where you put an element from capital G, and then take the identity from G prime and put that in the position where you put the identity from the group G prime. Okay, like so. And my claim is that this element of my set of all ordered pairs is actually going to be the identity in my group under the composition law that I've now defined. Okay, so quite simply to show that, we just need to think about what this composed with an arbitrary other element would be. Okay, so let's start with this on the left and then we'll look at on the right. Okay, so it will be on the left and we'll now take another arbitrary element of the group A prime here, and we now want to compose the two of them together, where this composition again is composition in our new product group. Okay, right, so what will this be equal to? Well, of course, we just multiply component-wise here, so we'll be composing the identity in G with the element A, and we'll be doing that in the group capital G, but of course, when we multiply the identity in G by any element in the group capital G, we'll just get that element back again, so the answer here will be little a. Okay, and again, for the second component, we'll be multiplying the identity in G prime by A prime, which is an element of G prime. Okay, and of course that will just give us A prime back again. Okay, so that tells us then that this ordered pair of the identity elements from the two groups will compose with this arbitrary other element from our product group to give that arbitrary other element back again. Okay, and hopefully you can appreciate that if I switch that round the other way, the exact same argument would hold true. Okay, so it is true that if I multiply with this on the left or on the right to any other element of the product group, that I will get that other element back again. Okay, so we do have an identity element. And finally, the final thing that we want to prove about these product groups is that we have inverse elements. So we want to prove that for any element of this group, any ordered pair in this group, that we do in fact have an inverse for it. Okay, now hopefully again this should be very intuitive. Indeed, product groups are far more easy to understand than quotient groups. Okay, so if we take an arbitrary element here, A prime, which is an element of our product group, G with G prime, okay, we need to prove that it has an inverse element, an element that will compose with it to give this element, the identity element here. Okay, so what is that element going to be? Well, what do we need in the first position? Okay, so I'll just write out our brackets here. So what do we need in the first position? Well, we need something that will compose with little a here to give the identity in G. Now, what is that element? Well, of course, it's just the inverse of A in the group capital G. Okay, that will compose with A to give the identity in G. So that will give us the correct first term here. Okay, and now in the second position here, we need something that will compose with A prime to give the identity in G prime. Well, of course, that's just the inverse of A prime in the group capital G prime. Okay, so quite simply, if you want the inverse element of any element of your product group, just take the inverses of the two components of your ordered pair here and put those in, okay, and then you'll get the inverse ordered pair basically in your product group. Okay, and just to spell this out even more, let's actually just look at what this element composed with A prime will actually be equal to. Okay, where this is composition in our product group, so I'll colour it in red again. We will just multiply A inverse with A, and we'll get the identity in G, and then we'll multiply A prime inverse by A prime, and we'll get the identity in G prime, which of course is our identity in this new product group. Okay, and of course this would hold true again if we multiplied it the other way around. So if we swapped these two over and did it the other way around, this would also hold true. Okay, so basically you give me an arbitrary element of this product group, I can find you an inverse element within this product group. Okay, so that then is how we can build larger groups out of two groups basically. You give me any two groups, I can construct you a larger group out of the two. Okay, right, so I think we'll call it there for this video. That's the formal definition then of a product group. In the next video, what I want to do is give you an interpretation as to what this really means, and then we'll have an example of actually constructing a product group.